All right, this is the voiceover for section 4.2. 4.2 starts introducing compound events. In the previous section 4.1, we had a single event. Hey, what's the probability of rolling a number less than 5? What's the probability of getting a question with 4 choices correct? Things of that nature. A single event. Now we move on to what's called compound events. Now within section 4.2, we're going to discuss two types of compound events. First involving the connector and the second involving the connector or. This, I will do this voiceover just for the and part, not the or. We're going to be using what's called the multiplication rule. In fact, the homework assignment is section 4.2, part 1, which introduces just the and portion. All right, we'll take up the or next time. Compound events notation. What's the probability that A happens in two trials? A happens first and B happens second. Probability in multiple events. Event A occurs in the first trial and event B occurs in the second trial. All right. We're going to solve these by using what's called the multiplication rule. You roll 2 dice. What's the probability you get a 5 on each die? Consider a collection of 6 balls identical in every way except color. There are 3 green, 2 blue, 1 red. You draw 2 balls at random from a collection without replacing the first ball before drawing the second. What's the probability that both of the balls will be green? You see that these two problems are nearly alike. They are alike in a sense that in each case, you are finding the probability of two events together. In the first problem, you got to find a probability of a 5 on the first die and a 5 on the second. In the second, you want a probability of a green ball in the first draw and a green ball in the second. However, the two problems differ in one important aspect. In the dice problem, the outcome of 5 on the first die does not have any effect on the probability of getting a 5 on the second die. When you roll a die, it's not like the die remembers what came out first. No, these events are called independent. What happens on the second toss of the die has nothing to do, the outcome there had nothing to do with what happened on the first rolling of the die. The die don't speak to one another, all right? These are purely what's called independent events. Two events are independent if the occurrence or non-occurrence of one event does not change the probability that the other event will occur. Independent. Rolling die. Drawing, well, I wouldn't say this. Rolling die, a woman having a child, a boy or a boy, or having two children. The sex of the first child has nothing to do with the sex of the second child. Independent events. In the problem concerning the collection of colored balls, however, the probability the first ball is green is 3 chances out of 6. There are 6 total balls, 3 of them are green. All right. If you get a green ball in the first draw, the probability of getting a green on the second changes, however, to 2/5. Because one green ball has already been drawn, there's only 5 left. Therefore, the two events of ball in the drawing problem are not independent. In fact, they're called dependent, since the outcome of the first draw changes the probability of getting a green ball in the second. So, hey, 3 chances out of 6, but once I take that first green ball, lay it to the side, well, now I've only got 5 balls left, and out of those 5, only 2 of them are green. If I did it again, put the second green ball off to the side, well, guess what? There's only 4 balls left, and only one of them is green. Dependent events. What does the independence or dependence of two events matter? Well, the type of event determines the way we compute the probability of the two events happening together, whether or not I have to adjust the probability of the second event to take into account what happened first. Hey, with rolling the die, one had nothing to do with another. All right, probability of rolling a 5 is 1 chance in 6 continuously. Doesn't change the probability whatsoever, but you can see here we're drawing the balls out of a bag. Probability does change. Two events are dependent if the occurrence of one of them affects the probability of the occurrence of the other. Doesn't mean necessarily means that it caused it, but it does affect the probability. Dependent events. Here's an example. There's one, two, three, four, five, six, seven examples here. And we're asked to find out are these events dependent or independent. Does finding your car radio work? Does that have any effect that your car headlights work, or vice versa? If you find your car radio doesn't work, does that affect somehow your car lights? Well, they both work off a battery. You get in the car, you turn the radio on, it doesn't work, and then you put your headlights on, that doesn't work. Well, guess what? You got a bad battery. All right, doesn't mean it caused it, but it surely affects the probability. All right, dependent events. This is supposed to be a joke. Number 7 is wearing shorts with black socks. Is that how affects someone getting a date? Well, the idea is, if someone's wearing black socks and sandals, maybe the girl would want to date him. It's kind of a silly problem. I would say dependent, but who knows? These days, maybe some women like plaid shorts and black socks with sandals. Does finding your cell phone work? Does that have anything to do with finding your car starts? Well, no, cell phone and car, nothing to do. Independent events. One has nothing to do with another. Finding your television works and finding your refrigerator works. Well, yeah, they both work on electricity. If you walked in the house, you turned your TV on and it didn't work, and you walked upstairs, there's a good maybe chance that your refrigerator's not going to work. Yeah, your power's out. All right, dependent events. Finding your calculator works and finding your computer works. Well, one has nothing to do. TI has nothing to do with your independent events. Randomly selecting a consumer from California, randomly selecting a consumer who owns a television. Well, you don't have to live in California to own a TV set. One has nothing to do with another. Number 12 was a different response years ago. In other words, you needed to have a computer to go on the internet. Well, now we know with mobile devices that's not the case. So these events would be independent. One has nothing to do with another because you can get on the internet without having a computer. That wasn't always the case years ago. Independent events. The basic multiplication rule is used for finding A. Find the probability if A happens first and B happens second. All right. If the outcome of the first event A somehow affects the probability of the second event B, you have to adjust the probability of B to reflect what happened in event A. This is the formal definition. The probability of A happening first and B happening second is the probability that event A occurs in the first trial and event B occurs in the second trial. The formal multiplication rule to find the probability of A happening first and B happening second is, hey, take the probability of A times the probability of B, given that A's already happened. Note, if these events are independent, probability of B given A is just really the same thing as the probability of B because you don't have to adjust anything if these guys are independent. It's like rolling a die twice and getting a 5 both times. One has nothing to do with the other. So in finding the probability of a 5 on the second toss of a die, you don't have to adjust anything. The fact that a 5 came out the first time, nothing to do with a 5 coming out when you roll the die a second time. A tree diagram is a picture of possible outcomes of a procedure shown in line segments emanating from a starting point. These diagrams are sometimes helpful in determining the number of possible outcomes in a sample space if the number of possibilities is not too large. All right. Guessing. A quick quiz consists of a true false question followed by a multiple choice question. All right. So there are 5 possible answers for the multiple choice question. It says consider the events of being correct on the first event and being correct with the second event. Are these 2 events independent? Well, a true false question has nothing to do with answering a multiple choice question. All right, so these events are independent. What's the probability of both answers being correct? Well, true false question with 5 answers, probability of getting it right is 1 chance in 5. All right. Probability of getting a true false question right is 1 chance in 2. 2 possible answers, true or false, and only one of them is correct. So 1/5 the probability of getting a multiple choice question right times multiplication rule times 1/2 probability of answering a true false question. Probably getting them both correct would be 1/5 times 1/2 or 1/10. Now he does the same problem, but he uses a tree diagram, all right, to get to the same answer. So first time out, the true-false question, you could answer it true or you could answer it false. If I answer it true, I've got 5 choices for the multiple choice. And here they are there. True A, true B, true C, true D, true E. Or I could have answered the multiple choice question as a false, and then once again, I've got 5 choices for the true-false. If I count the number of items in a sample space, there's 10 of them. But only one of those is going to be the correct answer. One chance in 10. Hey, same answer we got when we multiply 1/5 times 1/2. And it saved us the hassle of drawing this tree diagram. This is what's happening here. This is how we did it. Probability of getting a true false times the probability of getting the multiple choice question. Okay. Suppose you are to throw 2 fair dice. What is the probability of getting a 5 on each die? Well, these are independent events. All right. So all we need to do is find a probability of a 5 on the first die and a probability of a 5 on the second. One has nothing to do with the other. They're both 1/6. 1/6 times 1/6 is one chance out of 36. Excuse me, my wife is calling me from the grocery store. Okay. Hello? Yeah, what's up? Why did I say TheraBand for what, Brenda? I know what you're talking about, to be quite honest, man. I have no idea. I'm in the middle of sorry about that. He's asking me a question. I have no idea. Guys, when you get married, oh well. All right, one chance in 6 times one chance in 6 independent events. I didn't have to adjust the probability of the second event to take into account the first because the die don't talk to one another. In fact, I got a 5 on the first die. Nothing to do with me getting a 5 on the second die. 1/6 times 1/6. All right, so here's that rolling the die. If you're rolling 2 die, there's 36 equally likely outcomes. A 5 and a 5. Another way of figuring this out was it probably be getting a 5 on the first roll and a 5 on the second. A 5 and a 5. Only one way that can happen is a total of 36 ways. One chance in 36. All right, so that looks just like the answer we got here without having to go into that shot. All right, consider a collection of 6 balls identical except in color. Identical meaning they're the same size. One's not bigger than the other. 3 green ones, 2 blue ones, 1 red one. Compute the probability of drawing 2 green marbles from the collection if the first ball is not replaced. Here's the deal. If they want you to replace the first ball back into the mix, they will always tell you that in the problem. If he doesn't mention anything, you consider it to be without replacing. All right, so if it's not replaced, these events are dependent. Probability of the second thing happening has to be adjusted to account for the first green ball being picked out of the bag. Reason being, second time you go to draw a marble out, there's less of them and there's less green ones. The first time out, you've got 3 chances in 6 of getting a green. Second time out, if you put that first green one off to the side, not replacing it back into the bag, there's only 2 green ones. There's only a total of 5. If I did it again, it would be only 1 chance in 4. All right, multiplication rule, dependent events. I had to adjust this probability to take into account what happened first. So all you can see here with this chapter 4, you got to use some deductive. You got to think. You just say it that way. All right, you just can't put the first thing that comes to your mind. Oh, yeah, I'm off in it. Here it is. No, you've got to do some thinking. And you get better at thinking by doing these problems and working them out. So it's not just yeah, first thing that pops in my mind, I'm putting down. It ain't going to work. All right, here's an unusual one. Sometimes in these problems, you're not giving a raw count, but you're given a percentage. All right. He says, hey, the manufacturing process has a 70% yield, meaning that 70% of the products are acceptable and 30% are defective. Three of the products are randomly selected to find the probability that they're all acceptable. Well, what's happening here, these events are really dependent. All right, because you pull one out and then you go and draw another one. Well, you've there's less to draw from because you pulled one out already. The problem is that you're given percentages, so it's not correct to take 70% probability for the first acceptable product and then subtract 1%. 1% does not equate to one item. So what happens here is when you're given percentages, it actually becomes an easier problem for you, right? So the probability of getting a acceptable one first time out was 0.70. And guess what you do? You keep that same percentage all the way through. Even though these events are dependent, you think independent because it's not giving you a raw count. It's not like you get six marbles or 10 whatever. He's giving you percentages. So actually this works to your advantage. When you're given a problem that has percentages, even though the problem is theoretically a dependent or problem where you should be adjusting the probability of the second and third, because of percentages, you can get away with just using that same percentage all the way through. So it makes it somewhat easier for you. That only happens when you're given percentages. This is not raw counts. You think um, independent when in actuality they are dependent. All right, many times you're given the information in a chart form. Now, first thing when you're doing here, this problem here talks about positive results. People taking a lie detector test. All right, a false test. You have what's called a false positive. Machine says you lied and you really didn't lie. Or a true positive. You lied, the machine busted you. You get a true negative. The machine says you did not lie, and guess what? You weren't lying. A false negative is when the machine says that you lied, in actuality you didn't. All right, so first thing I need to do here is to get some, well, I guess I'm not doing it just yet. This is the same slide as the previous one. Here's what he's asking us. Hey, find a probability that the first subject had a positive test result and the second subject had a negative test result. Well, what's missing here is totals, all right? This probability is favorable over total. So the first thing I'm doing, I'm adding down and I'm adding across. I got 47 people who did not lie. I got 51 people who lied. I have 57 people who had a positive test result. I had 41 people who had a negative test result. All I'm doing is adding horizontally and adding down vertically. All right, so first time out, what's the probability of getting a person with a positive result? Well, how many people had a positive result? 57 out of 98. How many people had a negative result? Well, there's 41. But guess what? I haven't got 98 people. I've only got 97 because that first person I took out of the mix, the person who had the positive result. These events are dependent. All right. First time out, 57 people had a positive result out of a total of 98. How many people had a negative result? There it is. It's 32 and the 9, 41. The problem is there's not 98 people left. There's only 97 people. If I did it again, it'd be only 96, 95, and so forth. All right. So here's a case where you had to adjust the denominator in this second event here. Multiplying these two out, calculator will give you a nice decimal. Got to do some thinking. First thing you're doing is, hey, are these events independent or dependent? If they're dependent, I got to think about what happened first and how that affects what's going to happen in the second event. If they're independent, no big deal. These word problems, and that's what pretty much the statistics is all about. A lot of word problems. You got to be able to read and decipher what's going on. He starts out here talking about pacemakers, and each year there's a quarter of a million of these things implanted. I'm not sure those numbers are correct. He goes on to talk about the failure rate and the company that makes them. Well, anyways, all this kind of is gobbledygook. The problem really starts right here. It says, let's consider a small sample of 5 pacemakers, including 3 that are good, denoted by G, and 2 that are defective, denoted by D. D for defective, G for good. Find a probability that the first selected pacemaker is good and the second is also good. Part A, he says, assume replacement, which means I pull one out, then I put it right back in again. Well, if I put it right back in, I'm starting all over again. Part B says without replacement, I pull the first bad one out and I leave it out. All right, then I find the probability of the second one being defective based upon the first one being defective. So there they are, G, 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 D, D. All right, so with replacement, probability of getting a good one is there's three good ones out of a total of five, 3/5. I put that one good one back into the mix. Well, guess what? Second time out, getting another good one probability is same thing. Three chances out of five. There's three good ones and there's five. 3/5 times 3/5, 9/25, 0.36. Second, doing the same problem, but now considering you didn't replace the first one. The first time out, there are three chances out of five of getting a good one. I pull that to the side. I go back in the second time. Guess what? There's only four now left because I've taken that one good one out. And guess what? Out of those four, only two are good. If I did it again, it'd be one out of three. I couldn't do a fourth time because there's only three good ones to begin with. Right? So you got to be consider: are these events dependent or independent? Makes a big difference. Here's that same chart with the people taking a lie detector test, polygraph test. If two out of the 98 subjects are randomly selected without replacement, he didn't have to tell me that. If he didn't say anything, I couldn't assume that. If he doesn't say anything, I'm assuming without replacement. Find a probability that they both had false positive results. Well, let's see. Once again, I'm doing my totals. False positive results. Well, there are 15 people here who had a false positive. 15 out of a total of 98. I take that first person, I put them to the side. Well, guess what? There's only now 14 people who had false positives out of a total of not 98, because I took one out. It was only 97 people, 14 out of 97. In this particular textbook, if the probability is less than 0.05, we consider that to be unusual. So 0.0221 is less than 0.05. So in a polygraph test, it'd be unusual to have two people have false positives. I'm not even sure that polygraphs are even used in some states in trials because of the fact you get false positives, false negatives, and the like. All right, now we want the probability that three out of these 98 without replacement all had false positives. Well, same idea. It's going to be, here's my totals. Starting out 15 out of 98, then there's only 14 false positives out of a total of 97 people. Then there's only 13 out of a total of 96. If I did it again, it'd be 12 out of 95, 11 out of 94. You get the idea. Well, if getting two people with false positives was unusual, getting three people is definitely going to be unusual. It's an arbitrary figure. If something, the probability of something is less than five chances out of 100, we call it unusual. All right, blood types O, A, B, AB, Rh positive, Rh negative. Part A says if two of the 100 subjects are randomly selected, find the probability that they're both ORH positive. Well, there's 39 people out of the 100. All right. So if I do that with replacement, it's 39 out of 100 first time out. But then I put that person back in the mix. Guess what? Probability is still going to be 39 out of 100. Without replacement, it'd be 39 out of 100, followed by only 38 out of 99, followed by, if I did it again, 37 out of 98, and so forth. All right, BRH negative. BRH negative, there are two people. All right, so if I'm drawing three subjects, what's the probability they're all BRH negative? Well, I can't get three because there's only two. All right, so without replacement, it couldn't be done. It'd be zero because there's only two people. With replacement, it'd be 2 out of 100 times 2 out of 100 times 2 out of 100. I keep putting that person back into the mix with replacement. Without replacement, I couldn't very well get three people that are BRH negative because there's only two of them to begin with. This here talks about you folks into nursing, blood types, and the like. How that all rates the coronavirus. I don't know. All right. So notice I can't get three people. right? Because there's not a third person. It's BRH. Acceptance sampling. When companies produce things, they're not going to check each and every item. You would think they would do it with a pacemaker or whatever. A lot of things they produce, they haven't got the time or the money to check each one. They do what's called acceptance sampling. They take a certain sample of all of those products, and they let the whole shipment go. All right, so here's a case where the Tektronix company manufactured 400 backup power supplies. 8 are defective, and 3 units are selected for testing. Well, right away, you get 400 backup power supplies, and 8 are defective. Already I'm thinking, what isn't he telling me? If I have 400, 8 are defective. Well, 400 subtract 8 must be 392 that have no defects. And invariably, it's that 392 that you're going to have to work with. But he doesn't tell you that. But how hard is it to figure out? If 8 are defective, you have 400. Remaining 392 must be good ones. He's asking me if I pull out 3 of the units, what's the probability that the entire batch will be accepted? Well, what's the probability that all 3 are good? If all 3 are good, we're going to ship the entire batch of 400. All right, so first time out, no, it's just 392. It wasn't in the problem. I had to take the 400 total, subtract the 8 that were defective. Hey, 392. The remaining ones are good. So first time out probability is 392 out of 400. I pull that one off to the side. Guess what? There's only 391 good ones out of a total of 399. Third time I do it, it's 390 out of 398. If I did it a fourth time, it'd be 389 out of 397 and so forth. So this isn't bad. Your calculator will do this. All right, all you have is 3 fractions. All right, the Wheel and Tire Company produces a batch of 5,000 tires, and 200 are defective right away before I even start reading anything else. If I get 5,000 tires, 200 are defective, that must mean the remaining 4,800 have no defects. He's not telling me this, but I know you get the idea. There's always a little piece missing. The piece missing is you got to be thinking deductively. Have your head screwed on right. Take the 5,000, subtract the 200. Hey, 4,800 have no defects. The 4 tires are randomly selected. What's the probability that they are all good, which means they don't have any defects? All right, so what do we got here? 4 tires. So first time out, it'd be 4,800 out of 5,000. All right, 4,800 are good ones over 5,000 total. Take that one, put it to the side. 4,799 over 4,999. Third time out, 4. So you get the idea. Now this becomes a little cumbersome, right? Because these fractions are really big. Now what makes this even crazier is what if he told us if I drew 100 ties, picked 100 ties, what's the probability that they're all good? Well, I really don't want to do this 100 times. I was a little perplexed in doing it 4 times. So here's what he says here. I don't want to do this thing, 4,796 out of 4,996 and 479. My gosh, I can't even read it without getting tired, let alone doing this 100 times. So here's what he says here. He says, sometimes we treat things that are dependent as being independent, very similar to when we're given percentages. All right, 70% of the whatever are good or 70% defective. Even though the problem is intuitively a dependent problem, we're going to treat it as independent. And obviously, doing this 100 times, all right, doing this 100 times, doing all this 100 times would be considered, I guess, to be cumbersome. So what I'm going to do here is to treat this problem letter B as these events as being independent. One has nothing to do with the other, which means I'm going to use 4,800 out of 5,000. All right, 100 times. It's as if I took that good tie and put it back and drew it again and put it back. All right. So where am I getting this 0.96? Well, if I take this fraction, reduce it to change it to a decimal, 4,800 over 5,000 is 0.96. Now I want to do this 100 times because I'm picking 100 ties. Well, the fastest way to take a number and multiply it by itself 100 times is to take that number, in this case 0.96, raise it to the 100th power. You know, your TI-80 calculator on that last row, you know, it's called a caret. It looks like a V. You put the number in, you press that caret key, and then put in 100. I'll show you how to do that. This video is very easy on YouTube, how to raise something to a power on the TI. All right, so if it becomes cumbersome, all right, and it's called the 5% rule. 5% meaning, you know, we're drawing 100 ties out, 100 out of 4,000, 5,000 ties is less than 5%. All right, there it is for the multiplication rule. All right. When you're asked to find a probability of this happening first and something happening second, we use the multiplication rule. What we're going to see next time out is what's called the OR problem. All right, what's the probability that event happens first or event B? In one trial, what's the probability of event A happening or B happening? So when I have an and problem, I multiply. When I have an or problem, we're going to find out that we're adding. If you have an and problem, this happening and that happening second, and you're adding, you're doing it wrong. And goes with multiplication. We're going to find out that or goes with addition. We'll encounter that next time out. So you can get the idea. This has changed dramatically from, you know, what's the probability of me drawing a 3 or 5 or an ace of clubs. These are compound events. You really have to think your way through this.